Hello everyone. I'm Shivam Navle.
Myself, Ritesh Patil.
Myself, Amar.
And mini project title is audio watermarking using discrete wavelet transform, that is DWT. We have done this in MATLAB. In this project, we have demonstrated how a secret text message can be securely embedded into a audio signal using wavelet-based watermarking techniques. In our project, we have used the text ritesh, Shivam, Amar, that are our names. So our project aims to show how signal processing can be applied for digital right protection, authentication, and data hiding.
The main objectives of our project are to understand how discrete wavelet transform can decompose audio signals into frequency bands, to embed a text-based watermark inside a low frequency coefficient of the audio, and to reconstruct the watermark audio signal that sound identical to the original, and to extract the hidden message back and verify its accuracy. Finally, to evaluate system performs using bit error rate. What is the marking? Means the audio watermarking is a technique embedding hidden data into a audio signal so that the watermark is inaudible at it detectable later for verification of ownership. Basically, why we use DWT? DWT separates an audio signal into approximation and detail coefficient. The approximation part represents low frequency, which is particularly important and stable. By slightly modification of approximation, we can embed data without audible direction. This makes DWT watermarking robust, imperceptible, and reversible.
Our project has basically three main stages. The first is watermark embedding. So in the first step, we convert watermark text into binary bits, apply level 1 DWT on original audio, modify approximation coefficient that is CA based on each watermarking bit, then reconstruct the audio signal using inverse DWT and save the audio watermark file into the system into our device. The second part of our project is perform DWT to get the watermark extract to do the watermark extraction. Perform DWT again on watermark signal, then compare with original coefficient of extracted bits, then convert extracted bits back to characters. The third part would be evaluation, that is compute error bit rate (PER), visually compare binary streams and message. So from here we will direct to our MATLAB code and show how we have done our code in MATLAB. So this is our MATLAB code. We will explain the MATLAB code step by step. Yeah, the first step in our MATLAB code is to read the original audio signal. The name of our file is file example wave1mg. This is a 5-second audio signal which we are going to watermark. So the first step would be the read the original signal. The step two would be generate watermark. We are using message Ritesh Shivam Amar. Uh, so here is our we have given watermark string Ritesh Shivam Amar. So now the each 8-bit representation characters are converted into ASCII values. The ASCII values. The step three would be to apply DWT. Okay, go. So this is our MATLAB code. We have done implementation in MATLAB of our file. So we are going to explain our MATLAB code step by step. The first three are the basic function, that is clear CLC, clear and close all, which basically clears command window. We basically write it before start of the code. Then the first step is to read original audio. We do this using function audio read. We have used try catch, a safe block, attempt to read the audio. If it fails, shows a user-friendly message and rethrows the error for debugging. Audio is an array of sample n cross C, where C is in channel, Fs is the sample frequency. Display inside catch prints error message hint if read fails. Rethrow me forwards the original error so you can see the exact burial cost in MATLAB. So then the audio equal to audio semi colon comma 1 is the file is stereo to column. This selects the first channel left, makes the signal mono for simplicity. N is equal to length. Audio stores the number of sample used later to trim or reconstruct signal. Then comes our step 2, that is generate watermarking from string. Uh, watermark is equal to string. The secret message will be embedded in this code. We have taken our names as the secret message, that is Ritesh, Shivam, Amar. Then we go to the part of we have written unit 8 that converts characters in the characters of our name, that is RIT example into ASCII values. For example, ASCII value of 8 A is 65. So this converts the into ASCII value. Then our DWT to B ASCII value comma 8 left MSB converts each ASCII value into 8-bit binary row. This 8 forces 8-bit representation. MSB means the leftmost bit is the most significant bit, standard ASCII order. Binary matrix will be a M cross S, where M is the number of characters, that is number of characters in our string. Our string is Ritesh, Shivam, Amar. So then the binary matrix the matrix of bits aligned column wise for reshape. The function reshapes flattens all bits into a single row vector. For example, character 1 bit as character 2 bits in sequence. Then comes our WM length, stores total number of bit should be 8 cross number of 8 cross number of characters. Display prints the bit length so that you know how many coefficient you will modify. Then comes the visual watermarking part. The figure opens a new figure, subplots. These are the basic MATLAB commands. We are plotting the ASCII value representation and their binary representation in the form of graph. Then comes our part 3, perform level 1 DWT, that is this discrete wavelet transform. DWT audio comma har computes a single level discrete wavelet transform using the har wavelet. CA is equal to approximation coefficient. DA is the detail coefficient. Will be This will be embedded watermark bit CA because low frequency parts are more robust and perpetually important. Then the step 4 in our audio watermarking will be embedded watermark, that is alpha. Alpha is the scaling factor for embedding. It determines how much you shift a coefficient for bit. Small alpha represents less audible distortion, but watermark may be fragile in this case. Then large alpha, that is stronger watermark, possibly audibly artifacts. Then CA mod is equal to CA initiates modified coefficient with original values. The loop, we have written a loop for bit 1, add alpha to ith coefficient. For bit 0, subtract alpha from ith coefficient. This is bipolar embedding scheme, positive change for 1 and negative for 0. No, this code assumes CA as the least WM length coefficient, usually true, but you should check safety for real systems. Then step 5 would be reconstruct watermark audio. the IDWT CA mod comma CD comma har inverse DWT reconstructs the time domain signal from modified approximation CA mod and original detail CD. Watermark audio is equal to watermark audio 1 colon n ensures the reconstructed audio has same length as original. IDWT can return slightly different length, so you trim or pad accordingly.
So this is a now step 6, and this stage, save and play watermark audio. In this path where the watermark file will be saved, an audio write that writes the watermark audio array to the file with the sampling rate, and this display prints the confirmation with the path. Now the sound watermark audio of QFS plays the audio through your system speaker. Then pause the script execution until playback completes. Length is audio duration in seconds plus one adds a small margin. So now step 7 is in this stage we visualize the original versus watermark audio. We compare the both original and watermark audio graphically and other. So in this we opens now a figure there we see two plots. The top one is the original waveform in blue and the bottom one is the watermark waveform in red. So visual comparison shows that the waveforms are nearly identical. Watermark were intended to imperceptibility. You can zoom in. Example, now you zoom to see the small difference on that graph. So in step 8, we extract the watermark. So in this stage, we read back the saved watermark file into W audio, apply a single level discrete wavelet transform to the watermark audio to get the coefficient of approximation. So in this approximation coefficient of watermark audio. So in this, they initialize the extract one as a zero vector to store recovered bits. For each bit, position is I, and compare the coefficient of approximation I and original coefficient of approximation. If we compare the coefficient of approximation of I is greater than the coefficient of approximation I, we assume a 1 was embedded because embedding added plus alpha. Else, then assume we embedding subtracted alpha. This simple comparator recovers the embedded bipolar fix. Then this extraction assumes you know the original coefficient of approximation. This is non-blind watermarking that requires the original signal or its coefficient. Blind schemes don't need the original. So in step 9, we evaluate performance and verify the signal. So we compare original and extracted bit vectors element wise and returns one for mismatch. So sum counts the mismatches is equal to the number of bit errors and bit error rate is equal to error divided by total bits. But that is the performance metric. Lower is better. And if printf prints the uh, bit error rate and counts. So we reshape the and groups the extracted bit stream into rows of 8 bits. Each row is equal to one of character. Then transpose so expect rows. And this by 2D converts each 8-bit row to its decimal as to ASCII code. And character these convert ASCII numbers back to characters. So in transpose because the by 2D returns column vector and print the original and expected string from for verification. And try catch handles the error if the bit length is not a multiple of 8 or if there are too many bit errors leading to invalid ASCII values. So in Next step, we plot original versus extracted binary watermark. So we plot the two graphs for this comparison and new figure showing. So the top one is the original bit stream and bottom one is extracted bit stream. The extract in a red. Visual way to spot mismatch and check where errors occurred. So final confirmation message is that. So in final step you added earlier in other version. Replot extracted message as text or as custom. If extraction succeeds, this plots numeric ASCII values of extracted characters and display the recovered text as a figure. Animation for easy visual confirmation.
After एक मिनिट हा, sorry. After the completion of project, we get conclusions that are the embedded and extracted text-based watermark using DWT in MATLAB. It can be achieved low distortion and very low bit error rate, and it demonstrated reversibility and imperceptibility. And the key achievements of the project is successfully demonstrated effective DWT based watermarking, achieving imperceptibility and low bit error rate, ensuring reliable copyright protection and authentication in audio signals.
Thank you everyone for watching this video.